Hi, welcome to another IGCSE physics video. Today we're looking at section 1.6, which is moments. In this video we will learn about moments, some applications of moments such as seesaws and wrenches, and we will also learn about equilibrium in moments. So what are moments? Generally, moments are defined as the tendency of a force to rotate an object about an axis. Now, mathematically, moments are defined as the turning effect of a force exerted on an object at a distance from an axis. So let's draw a diagram from an application to see what this means. Let's say we have this nut that is being tightened on a wall. And let's say using this wrench, we apply a force on this nut from here. We know that this is quite a distance away from the fulcrum of this system, which is at this point. So if we apply force at this part of the wrench, then we will gain the maximum turning effect on this nut. On the other hand, if we apply force on this part of the wrench, then the turning effect will be less as the distance is less from the pivot. This turning effect that we get by applying a force along a distance from the pivot of this axis determines the moment that we get. So we know that the moment is represented by the letter m, and moment is force multiplied by the distance from the pivot. So it's force with the symbol times the distance from the pivot, and that shows us the turning effect of this force. So here I have another example of demonstrating moments. So here I can see that this guy who's sad is trying to lift this boulder off this ground. And we know that this person has a lever to pull it off. So we can say that the pivot is over here because that is where the lever touches that boulder at the bottom. And we also know that the person is applying force with their arms at this point, and they're pushing it down so that the boulder can lift up from this side. Now if we know the value of the force that this person is exerting and the distance from the pivot that this person is applying the force, then we can calculate the moment that is being placed on this boulder. And we can see that this lever is going to turn in a clockwise direction. So we can say that this is a clockwise moment. Let's say that this distance d was 3 meters. And let's say that this force was about 100 newtons. Then we can calculate the moment of this force using this formula. So we know that the force is 100 newtons clockwise times the distance, which is 3 meters. And by looking at the units over here, we can see that we have newtons and meters. So the units of moment would be in Newton meters. So 100 times 3 is 300, and then we get the units. So the moment or the turning effect that this person is applying on this boulder is clockwise 300 Newton meters. But we still haven't discussed what happens if we have two moments that are being applied on an object. We have only discussed when there's a single moment on an axis on an object. So now we can see what happens when two forces are being applied along an axis and how two moments affect objects using seesaws. So here I have my seesaw, and there's two people that are sitting on the ends of the seesaw. In this situation, I can see that there are two moments that are being applied on the ends of the seesaws. On this end, let's say that this person's weight is applying a force on this end of the seesaw. And let's say that this person's weight is about 800 newtons. And let's say that this girl's weight is about 700 newtons. So this boy has a mass of about 80 kilograms, and this girl has a mass of about 70 kilograms. They're quite heavy. And let's say that the length of this seesaw is about 2 meters. So now that I know that these two people are sitting on the ends of the seesaw, and the distance along the axis of the seesaw is 2 meters, and the pivot is in the central point of the axis, I can calculate the magnitude of the moment or the turning effect and the direction of the turning effect for both of these people using the formula of moments. So let's calculate the moment of this boy. So we know the formula for moments, which is moments equals to force times the perpendicular distance from the pivot. So let's find the moment of this boy. mb for the moment of the boy equals to 800 newtons of force, which is the weight of this boy, times the distance from the pivot. So we know that the total distance of this axis is 2 meters, and we only calculate the distance from the pivot, which is half of 2 meters, meaning it's 1 meter. So the distance that the boy is sitting from the pivot is 1 meter, giving us that the moment of this boy is 800 times 1, which is 800 at newtons times meters or Newton meters. So the turning effect of this boy on this axis of the seesaw is 800 Newton meters. Now let's calculate the moment for this girl. So I'll say moment g for the girl equals to 700 newtons, which is the force, and in this case the force is the girl's weight, times the distance from the fulcrum or the pivot, which is 1 meter. And if we calculate this, we get 700 Newton meters. So here I can see that these two people have different moments or turning effects along the axis. Now since the moment on this side is in clockwise direction, and on this one it's counterclockwise, and this person has a greater turning moment, and this person has a greater moment, then we can say that this person will push the seesaw down, and this seesaw will push upwards by 100 Newton meters, which is going to be the net effect of this turning force. So I know that this boy has a moment of 800 Newton meters clockwise in this direction because the weight is pointed in this direction. And over here the weight is pointed at this direction, but it's on the left side of the axis, so the moment will be in the counterclockwise, and it's at a moment of only 700 Newton meters. Therefore, there's a disbalance in the moments, and we can find the net moment, which is going to be 800 Newton meters minus the 700 Newton meters from the girl, giving us a net moment of 100 Newton meters clockwise. Now, in another scenario, let's say that we had the girl weighing 800 newtons and the boy was weighing 700 newtons, so it's flipped. Then the moment of the boy would be 700 Newton meters in the clockwise direction, and the moment of the girl would be 800 Newton meters in the counterclockwise direction. So this time, if we find the net moment, I can see that it's going to be 100 Newton meters in this direction, or anti-clockwise. So the net moment in this case is 100 Newton meters counterclockwise. Now the final thing that remains in this situation is, how can we change something in this situation so that the fulcrum, it stays level and it doesn't have a moment in any direction? Well, we can do that if the moment on each side of the fulcrum is the same. So if this boy also weighed 800 newtons, then we would have an equal force on each side of the fulcrum. And if we had the same distance from this pivot for both of the people, then the moment for each of them would be the same. So in this case, we're talking about the equilibrium of moments. So here the moment of the girl would have to equal the moment of the boy, or the force times the distance of the girl would have to equal the force times the distance from the pivot for the boy. And now if we calculate that, we get 800 Newton meters equals to 800 Newton meters. And for the girl it's counterclockwise, and for the boy it's clockwise. And so the directions of the moments are balanced by the 800 Newton meters. So we can say that this pivot will keep this level and it won't turn. So we can say that the moments are at equilibrium and there's no net turning force on it. So the net moment would equal 800 minus 800 Newton meters, giving us 0 Newton meters. And so we're at equilibrium. And this is the end of section 1.5 for moments. I hope you found this video helpful, you understood the concepts of moments and equilibrium in moments and how we can balance things. I hope you found the applications useful. And leave a comment in the comment section and provide feedback so I can improve my videos in the future. And I'll see you in the next video, and thanks for watching.